Alright, so next thing I want to talk about is fields and energy and potential. So our two major equations for these modern forces, which I could in all honesty call field forces, is universal gravity, G(m)(m) r squared r hat, and our Coulomb's law, Kqqq over r squared, Kqqq over r squared r hat. Now all of those are representing forces. But let's say, dealing with energy was pretty simple. So I want to express these as energy equations instead of as force equations. If I can understand them as energy, then I'm better off. And then we have this idea of stability. If everything turns out to be negative, the system tends to be stable. If it all turns out to be positive, it turns out to be unstable. So it's nice to be talking about energy instead of forces. So I want to look at those equations. They're all force equations. How would I take a force equation and turn it into an energy equation? Well, maybe we should go back and look at the work equation. I mean, that turned a force equation into an energy equation. Well, the work equation was force times distance. And each one of these is representing a force. So all I have to do is multiply. Oops, I misspoke. Not distance, displacement. All I have to do is multiply this by displacement. Well, that displacement is actually pretty simple. It's r. Okay? So I've got force times radius, force times radius. If I substitute this in here and I bring it in, I substitute this into here, I get this equation, K, Q, Q, R. Oh, bring it down here, negative G, M, M over R. So look at that. I've got my KQQ over R, I've got my negative GMM over R. It automatically looks like if I have, well, looking at the should point over there. Looking at that one, KQQ over R, it looks like if I have a proton and an electron, I've got myself something that's relatively stable, depending on the kinetic energy. Remember, when we talk about stability, we're talking about total energy. The total energy turns out to be negative. The system is relatively, it's stabler. And it looks like gravitational force is always going to be stable. So we've got ourselves a representation. Look, we've got potential energy. Okay? So I've just developed energy equations, and I'm just going to put over here E. Okay? So those are all representing energies. Now I want to take that energy and I want to do something with it, but the first thing I want to do is like, let's talk about these as fields instead of as forces. So when somebody tells you, well, force fields, well, I'm standing in front of a force field, I'm going to be protected by laser beams. I want to talk about as fields, not necessarily force fields, but gravitational fields and electric fields. So when we talk about electric and gravitational fields, we're talking about the potential to have a force. The only way that you can have a force with those two equations is if you have two charges, two mass, two or more, I should say. If you only have one chunk of matter or you only have one charge, you don't have a force. You have what's called an electric or gravitational field. As a matter of fact, you can have multiple charges, each generating their own field, and you can come up with multiple, or you can come up with one big equation to talk about the electric field or the gravitational field. But the important thing to keep track of is that two charges make a force, one charge will make a field. So I want to come up with a field equation, and I want it to be the potential. If I drop the piece of matter into my gravitational field, I experience a gravitational force. If I drop the piece of charge into my electric field, I create an electric force. So how do I do that? Well, I'm going to take one simple property. I'm going to take these and I'm going to divide either by Q or by mass. Okay? So that's going to give me the potential, the potential for a force, not potential. Well, I'll explain what potential is here in a second. It gives me the potential to have a force. And what we call those are fields. Gravitational field, electrostatic fields. In some cases, even magnetic fields can be described that way. Magnetic fields are a component of a force. If we look at the Lorentz force, which is a little bit later, magnetic fields are potentials for forces. It's when you introduce a moving charge that you end up with a force. So they're all potentials. Okay? Or God, I keep using that word potential. They're all potentials for a force. There is a word potential. I'll get to it in a second. But these are potential for forces, and we call those fields. Okay? So blah, 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 divided by Q, divided by M. I get this equation, K, Q, R squared, R hat, or negative G, M, R squared, R hat. Important difference here. Energy, remember, is a scalar, has no direction. The R hats drop off when I do this multiplication. This is actually a dot product, and dot products take two vectors and turns them into a scalar. Over here, I'm dividing by a scalar, so when I divide by a vector by a scalar, I'm still left with a vector. So I end up with my force equations over there. So KQ are not my force equations, my field equations, but my field equations turned out to be vectors. KQ over R squared, GM over R squared, with the R hats to denote a direction. Okay? So I've got myself an energy over here. I got myself fields over here. I got myself forces over here. I want to introduce the last concept, the word potential. Now, when I refer to potential, I'm referring to this. When I was talking before about fields, I'm talking about potentials for forces that has its own term, fields. Electric fields, gravitational fields, magnetic fields. Those are all potentials for forces. Now we're going to talk about potential itself. Okay? Potential is the ability to have energy, much in the same way as fields is the ability to have a force. If I introduce a charge into a field, I have a force. If I introduce a charge into a potential, I have energy. So what I want to do is I want to do the exact same process for fields that I did for energy. Okay? So I did this for fields. I divided by charges and masses. Now I'm going to go ahead and I'm going to do the exact same thing for energy, and I'm going to come up with a new term called potential. Okay? Dividing by Q or dividing by mass gives me my potential equation. So if I divide by charge, I end up with KQ over R. If I divide by mass for my gravitational, I end up with negative GMR. Okay? So now I have my potential. Okay, these are what is called potential, not potential energy. It turns out that these are potential energy. Remember, the difference between kinetic and potential energy is that this is positional based. There's a position value here, a position value here, potential energy. This is what's called potential, which unfortunately the best way I can describe it is the potential to have energy. Okay? Cool. It's not quite energy. You introduce a charge or introduce a mass and you get yourself energy. Make sense? So, KQQ or KQ over R squared, negative GM over R squared, and I got my directions here. But look how simple it is to go from here to here. Look how they're all kind of related. If I multiplied this field, which here's my electrostatic field, times R, I get potential. If I take my gravitational field and multiply it by R, I get myself my gravitational potential. So they're all kind of related to each other. I can get from potential to field. I can get from potential to energy. I can get to energy to potential to force to fields. I can go all over the place because of this relationship. They're all interrelated to each other. They all can feed back into each other. I can go any way. I just have to learn which constants I have to multiply or divide by in order to get to whatever point I need to get. So if I'm given an equation, let's say, for the force, I can quickly turn that force equation into an energy equation. Or I can quickly turn that force equation, sort of, into a field equation. Okay? Does that make sense? So that's the interaction between energies, potentials, fields, and forces. So I've got force, I've got fields, I've got potential, and I got energy. Okay? So they're all related to each other. They all move around. They all interact with each other. It's really kind of interesting how that ends up. Cool? So that is potential, fields, and energy.